All right, here we are. This is lesson 5 for probability, mostly about tree diagrams. So here's a warm-up that will make you think about probability in a different way. 7% of RHS seniors attend PSEO, so the probability of PSEO for one kid is 7%. We're going to select students from the senior class. Find the following. A, select 10 seniors, at least one of them does PSEO. So this is can be challenging to count. At least one, so that could mean one kid has PSEO, it could mean 2, it could mean 3, 4, 5, 6, 7, 8, 9, 10. That's a lot of different things to try to count and then add up. So it's much easier in this context to count what we don't want. We're going to do this. We're going to count the probability that nobody is PSEO. So what's the probability of PSEO with a C? Remember, the C means complement. It would be it would be 1 minus 0.07, so 93%. So 93% of the kids do not attend PSEO. So if I wanted to pick 10 kids in a row and none of them have PSEO. So I'm trying to do 1 minus probability of 10 without PSEO. Okay, that would be 1 minus 0.93. Probability that they don't have PSEO is 93. And I want to do that 10 times over. Like, I want to do it twice, 3 times, etc. Well, that's a little silly. I'm just going to write 0.93 to the 10th power. If I just do 0.93 to the 10th power here, let me start there. That's about 48%. So that means if I pick 10 kids randomly, 48% of the time, none of them will be in PSEO. If I then do 1 minus that answer, that's about 51.6%. Okay, that would be the percentage of time at least one kid has PSEO. I don't know exactly how many have PSEO, but I know at least one does. Because 0.93 to the 10th power, that's the 48.3%. These are the groups that have 0 PSEO kids, right? And you're going to subtract that from 100. And all the other groups have at least one PSEO kid. So knowing that with part B, it's really the same exact thing. The only thing that changes is the number of kids. Now I'm doing 25 kids, so we put that there. And you got 83%. Okay, so 80.837. Mainly the idea of this slide is to teach you that often if you're trying to count what you're being asked to count and it becomes overly complicated and difficult, then typically that means you should count the complement. All right, here's the main heart of the lesson. It's talking about athletes and at the Olympics, and some of them took drugs to try to win, those cheaters. So we've got 10,000 athletes, 5,000 of them were drug tested. And here's the nitty gritty of it. 2% of the athletes have taken drugs. Okay. All right, let me just start there. 2% of the athletes took drugs. So I'm gonna make my tree go drugs, and this is 0.02, which means down here, these are people that that's a not symbol, did not take drugs, and that would be 98%. Every time your branch has a split, these two numbers have to add up to 1, or 100%, okay? All right, what? It goes on to tell us that false positive tests happen, okay? How often does that happen? It says a false positive is when it says you have a positive result, but you really didn't take drugs, okay? There's also false negatives. Okay, so let me go further in my tree. So these people could have positive or negative results. Positive plus, negative with a little minus, okay? The false negative would be this right here, this outcome. These people took drugs, but they got lucky. The test was negative. That's not a negative sign, Feig. Okay, this is a false negative. They got lucky. False positive is right here, this outcome. These people did not take drugs. Right here, they did not take drugs, but the test was positive. That's really unfortunate for those people. All right, now it gives us percentages for these. It says the false positive rate was 1%. Okay, so on my tree, this branch is 1%, which means this branch down here is 99%. Remember, every time you split, you get 100%. The false negative rate is 0.5%. That's right here. As a decimal, that's 0.005, which means this is 0.995, or 99.5%. Again, these two add up to 1, and these two also add up to 1. All right, I got my whole thing filled out. I've added in these questions down here that we're going to do. Oop, I left the answer to one of them there. Go away. First one, probability someone took drugs and they had a positive test. So that would be really which branch? That's drugs and a positive test. So to arrive here, first they had to take drugs. There's a 2% chance of that. And then they had to get the positive, and there's a 99.5% chance of that. So you need to multiply these two probabilities. You can think of them as back-to-back events. Probability of drugs, taking drugs, times the probability of a positive test, okay? And that would be what I just alluded to. It'd be 0.02 times 0.995. And that happens 0.0199% of the time. I'm going to put that over here in green. To get to this branch happens that percent of the time. The next one, not taking drugs in a positive test. So, whoops. That would be probability of not taking drugs times the probability of a positive test. We are going down not taking drugs in a positive test. In other words, what's the probability of getting here in the tree diagram? So that would be 0.98 times 0.01, which is 0.0098. So to get to a false positive, there's your percentage. All right. Then this question is piggybacking off of these two, okay? What's the probability that someone has a positive test? Well, we just found the two outcomes in the tree that are positive. Here's this probability to get here, and here's this probability to get here. So I simply need to add them up, okay? So 0.0199 plus 0.0098. I know the decimals are really annoying and cumbersome, but do your best. So 0.0297. It's about 3%. So 3% of the athletes had a positive test. Either they were in this positive test group or this positive test group, but together it was about 3%. 2.97%. Would you rather me write it like that? The next one is I want you to remember how to do the formula for conditional probability. The numerator is the probability of both of these things occurring. Okay? Taking drugs and a plus sign for positive test. The denominator in this situation is always the probability of the condition, right? The condition is a positive test. Now, don't start over, folks. We already found both of these things. We found it right here and right here. We already have it. So I'm just going to write them down in fraction form and then use my calculator to divide them. So one more time to help you out, let's color code this. Probability of drugs in a positive test is right here because it's right there. And then the probability of a positive test, we did that right there, which is that decimal. If I then just divide them, I have my answer. It's about 67%. All right. Are the events of a positive test, I should say and taking drugs, are they independent? Let's just explain this one because I think it's fairly intuitive. Does taking drugs have an effect on your test? That's how I would. Does taking drugs have an effect on the test? And the answer is clearly yes, it has an effect, right? Look, if you take drugs, you're going down this path. You end up here with these percentages for your test. If you don't take drugs, you're going down this path. And you end up with these percentages for your test. Essentially, the fact that these percentages are different than these percentages means that these are not independent. The test does not have the same probability for drug users and not drug users. So that means these are dependent events. These are dependent because taking drugs has an effect on the probabilities of that person's drug test. All right, folks. Enjoy that lesson. Bam.